Yeah. Good evening, guys. Are you able to hear me? Are you able to hear or not? Okay. So today we'll get started with the next chapter, chapter 13, that is nuclear, right? If you see what is nuclei, nuclei is basically the plural form of nucleus. So if you see the previous chapter, in that chapter we were concerned only about the atoms, means we were concerned about the structure of the atoms. Am I right? So we saw what are the different structures of atoms that were proposed to us. And then in that, one of the parts that we got was nucleus. This we came to know from the Rutherford's experiment, right? So in this chapter, if you see, our concentration is mainly going to be only about the internal part that is called as the nucleus. Okay. So here we are going to, guys, I need a confirmation if you're able to hear me or not.
Yes, sir, we can hear you.
Okay. Okay. Now we'll write down the important points. So first we will see the introduction part to it. So the introduction part I have already given. So compared to the previous chapter, during the alpha ray scattering experiment, the term nucleus was coined for the first time, right? And it told that the whole mass of the atom and positive charge is concentrated in a central core termed as nucleus. And the third part is, it is understood that the of dimensions of nucleus is much smaller than the overall dimension of the atom. Right? And lastly, we know the fact that nucleus is surrounded by This nucleus is surrounded by orbiting electrons. So these are all the important points related to the introduction of this chapter. Okay. So moving on to the next part. Now we are going to see the important points related to nucleus. First, nucleus consists of the elementary particles like protons and neutrons, right? Which are collectively called as nucleons. Second, if you take a proton has positive charge of the same magnitude as that of the electron, and its rest mass is about 1836 times the mass of an electron. So if you're done with this part, let me know. Done? Third, a neutron is electrically neutral, whose mass is almost equal to that of proton. So here, an important point to be noted is charge of proton is equal to charge of electron. Whereas if you talk about the mass of proton, that is equal to the mass of neutron. Now the next question is, we know that inside a nucleus, you have nucleons. The question is, how are these nucleons held together, right? So the nucleons inside are held together by strong attractive forces called nuclear force. And the fifth point is, if nucleus of an element is represented by X, A, Z, then X is called as the chemical symbol. Z is atomic number. Z is atomic number, where we know that atomic number is basically represents the number of protons, which represents the number of protons. And A represents the mass number, which represents number of nucleons. That is protons plus neutrons. So make a note of this point. Done? Now, the sixth point is number of neutrons, that is capital N, is represented by A minus Z, where it is the difference of mass number and atomic number. And the seventh point about nucleus is, it's an example that we can discuss. For example, if you have this chlorine atom or the chlorine element, so if it is having the mass number to be 35 and atomic number to be 17, then the number of neutrons is going to be 35 minus 17, which is going to give us an 18. So this has 17 protons and 18 neutrons. As a whole, it has 35 nucleons. So this is all about the nucleus part. Next is the classification of nuclei. First, we call as isotopes. So what are isotopes? So isotopes are atoms of the same element having the same atomic number Z, but different mass number capital A. So this is the definition. Secondly, if you look at the examples, isotopes of hydrogen, they are represented as H11, H21, and H31. They have the same atomic number but different mass number. So in other words, how can we say? In other words, they have the same number of protons, but different neutrons. And lastly, what you can say is, as the atoms of isotopes have identical electronic structure, they have identical chemical properties. Hence, placed in the same location in the periodic table, is there any doubt till here? So can I assume that there is no doubt? Okay. The second classification is isobars. Isobars are atoms of different elements having same mass number A, but different atomic number Z. So if I look at the examples of isobars, it will be oxygen 16 and nitrogen 16. They are said to be isobars because they have the same mass number. Sorry. And nitrogen 16 with the atomic number being 7. So they are said to be isobars because they have the same mass number but different atomic number. And also, if you observe, they are two different atoms. Oxygen and nitrogen cannot have the same chemical properties, right? So from this, we can conclude, since isobars are atoms of different elements, they have different physical and chemical properties. And the next part that we have are isotones. So we would have seen isobars, Z is same. Sorry. So we have seen isotopes, Z is same. Isobars, A is same. So isotones A minus Z should be the same, which is nothing but the number of neutrons. So isotones are atoms of obviously different elements having same number of neutrons. And if you look at the examples of them, carbon 14, 6 and oxygen 16, 8 are the examples of isotones, because here if you see A is 14 minus Z is 6, which will give us 8. Similarly, 16 minus 8. This is also going to give us 8. So they have the same number of neutrons. So this is all about the different classifications of nuclei as isobars, isotopes, and isotones. So is there any doubt till here? Is there any doubt?
No, sir.
Okay. So shall I proceed? The next topic is about general properties of nucleus. The first one is called nuclear size, right? So the concept of nuclear size came into picture only after the Rutherford's experiment. So according to alpha particle scattering experiment, the distance of closest approach, the distance of closest approach of alpha particles to the nucleus was taken as a measure of nuclear radius. Which is approximately 10 to the power of minus 15 meter, or it is also called as 1 femtometer. And in the same thing, if nucleus is assumed to be spherical, then an empirical relation is found to hold good, which gives the relation between the radius and the mass number capital A, right? And see, if I take this to be the nucleus, and if it is assumed to be spherical, then radius is observed to be directly proportional to the mass number raised to the power 1 by 3. That is the cube root of mass number. And from this, if you remove the proportionality, we can say R is equal to R naught into A power 1 by 3, where R naught is called the constant of proportionality, which is equal to 1.3 F or 1.3 into 10 power minus 15 meter. So capital F here represents Fermi. Fermi. So this is the first property that is associated with respect to the nucleus, that is the nuclear size. Similarly, if you are done copying this, I'll go to the next property. Similarly, the second property that we are going to see is called as nuclear density. It is represented by the symbol rho and a subscript n. So, nuclear density rho n can be calculated from the mass and size of the nucleus, where rho n will be equal to nuclear mass divided by nuclear volume. So it is like how we define mass density. Mass density is defined as mass by volume. Since this density is specific with respect to the nucleus, we call it as nuclear density. Hence, it is defined as the nuclear mass divided by the nuclear volume. Now, if you take the nuclear mass, then we can understand that the nuclear mass is contributed by the mass number. So, A times mass of each neutron is going to be the nuclear mass, where A is obviously the mass number and Mn will be equal to the mass of neutron.
Sir,
Yeah,
shouldn't it be mass of nucleon?
neutron and proton have the same mass, no? That is why I wrote mass. So you want to write it as nucleon? That is right. Okay, I'll correct it. I'll not say correction, I'll changing it. Because you remember this point, I'll show you weight. What did I tell you here? I told you here, mass of proton is equal to the mass of neutron. Right?
Okay.
So proton and neutron are collective. The collection of protons and neutrons is called as nucleons. So when I say nucleon, I can either be speaking about a proton or a neutron. Nitish, I hope it is clear. So that is why I wrote mass of neutron. But if you want, we can write it as mass of nucleon also. So A is the mass number and Mn represents the mass of each nucleon. Mass of each nucleon. Okay. And remember, the mass of each nucleon is approximately 1.67 into 10 power minus 27 kilogram. So this is a value to be remembered. So it is 1.67 multiplied with 10 power minus 27. So having this in mind, if we see rho n, then rho n will be equal to nuclear mass divided by nuclear volume. I'm rewriting the formula again. So when I talk about mass, it is going to be A times m into n, the whole divided by. The nuclear volume is going to be 4 divided by 3 pi r cube, because nucleus is assumed to be a sphere. But according to the previous general property that we saw, we know that R is equal to R naught into A power 1 by 3. I'm sorry, R is equal to R naught into R is equal to R naught into A power 1 by 3. Right? If I take this value and plug it here, then I'll get rho n is equal to A times m into n divided by 4 by 3 pi into R cube is R naught A power 1 by 3 the whole cube. So this will be equal to A into Mn divided by 4 by 3 pi into R naught cube into A. So if you see A and A will get cancelled, which implies rho n will be equal to 3 by 4 pi into Mn divided by R naught cube. Now if you observe this expression, 3, 4 pi, Mn and R naught, everything is a constant. So from this, we can conclude that the density of the nucleus is, or nuclear density is always a constant. Right? So substituting all the values, we get rho n is equal to 1.816 into 10 power minus 17 kilogram per meter cube. Right? So which we can say is almost a constant for all the nucleum. Irrespective of whom? Irrespective of the size of the nucleus, irrespective of the size. Right? And most importantly, if you look at the value that is being given here, okay, one small correction, it is 10 power plus 17. So 1.816 into 10 power plus 17 kilogram per meter cube. Right? So having this in mind, we can say, look at the value, it is such a big value. From this, we can conclude that the nucleus, or I can say the nuclear matter, is in an extremely compressed state, is in an extremely compressed state. And why is it happening? Because of high value of nuclear density. Is this point clear? So please make a note of this. And let me know once you're done. Okay. Next. So the third property that we are going to see is nuclear charge. So logically, if you think inside a nucleus, who's responsible for the charge? It is the protons, right? So the charge of a nucleus is obviously due to the protons present in it. And we know that each proton has a charge equal to 1.6 into 10 power minus 19 coulomb, because this is the charge of an electron also. So if an atom has Z protons, then the nuclear charge is given as Z times E. And this is also a value to be remembered. So the nuclear charge depends on the number of protons present in that nucleus. So the fourth property is atomic mass unit, which is also called as AMU. So generally, when you take the mass of the nucleus, it is not expressed in terms of kilogram, rather it is expressed in terms of a unit called as AMU, because it is more convenient. So we can understand that it is convenient to express the mass of nucleus in terms of atomic mass unit, or in terms of AMU, though we know that the mass of the though we know the unit of mass is kilogram. Now the definition for atomic mass unit is, it is considered as 1/12 of the mass of carbon atom, that is C12(6). So if you are able to find the mass of carbon-12 atom in terms of if you're able to find the mass of carbon-12 atom and divide it with 12, that value will be equal to 1 AMU. So if you see, carbon of atomic number 6 and mass number 12 has a mass equal to 12 AMU. So this 12 AMU divided by 12 is what is going to give us 1 AMU. Okay. Now, an important point to be noted is one atomic mass unit is equal to 1.67 into 10 power minus 27 kilogram. So one atomic mass unit in terms of kilogram is given as 1.67 into 10 power minus 27. Right. Now, if you see, in the beginning, we discussed that mass of proton and mass of neutron are approximately the same. Okay. Yeah. So in the beginning, we discussed that mass of proton and mass of neutron are approximately the same. See, when you try to express them in terms of kilogram, right, they will appear to be the same. But see what will happen if you express the same values in terms of AMU. So if you take mass of proton So if you take the mass of proton as MP, its value is given as 1.007276 AMU. Similarly, if you take the mass of neutron, that is MN, then this will be equal to 1.008665 AMU. Right? Now, if you take So these are the two values. Now, if you observe these two values, right, are you able to see a small difference in their mass? So that is why they are approximately the same because AMU is a smaller quantity. So when you bring it to the smaller quantity, that is when we will be able to see the exact difference. Right? And it is also important that AMU will help us to find something called as energy equivalence. Okay. So when you try to calculate according to Einstein's equation, so according to Einstein's equation, if you observe, E is given as mc square, right? Where E is the energy, m is the mass, and c is going to be the speed of light. So if I try to calculate the energy mass equivalence of 1 AMU, right? Then you can calculate it like this. 1 AMU is approximately 1.67 into 10 power minus 27 kilogram. And we know that C is equal to 3 into 10 power 8 meter per second. So if you try to calculate the energy, it will be equal to 1.67 into 10 power minus 27 into C square, which is going to be 9 into 10 power 16. Right? So this value will be in terms of joule. Now what we will do is, we will calculate the energy mass equivalence of 1 AMU in terms of electron volt. So when you're trying to calculate in terms of electron volt, then E will be equal to 1.67 into 10 power minus 27 into 9 into 10 power 16 divided by 1.602 into 10 power minus 19, because we know that 1 electron volt is 1.602 into 10 power minus 19 joule. So this will be in terms of electron volt. And when you try to calculate this value, E will be equal to 931.5 into 10 power 6 electron volt, or this 10 power 6 electron volt can be called as 931.5. It can be called as mega electron volt or million electron volt, because 1 million is 10 lakhs, 10 lakhs is 10 power 6. Okay. This is a value to be remembered. Okay. So I'm assuming that you're clear, and then moving on to the next property, that is nuclear mass. So we saw nuclear charge. We know that protons present inside the nucleus are the ones responsible for the charge of the nucleus. Now the question is, who's responsible for the mass of the nucleus? And the answer is very simple. They are the nucleons. Right. Answer is very simple. What are they? They are the nucleons. Now, if you see, as the nucleus consists of protons and neutrons, the mass of nucleus is assumed to be mass of its constituents. Mass of its constituents. So if I take the assumed nuclear mass, then that will be equal to Z times mass of each proton plus A minus Z times mass of each neutron. Right? So it is going to be Z times mass of each proton plus A minus Z times mass of each neutron. Right? So here comes an important point to be noted. So the reason why we called it as assumed nuclear mass is because it is not the actual nuclear mass that is going to be present. So when you take the same nucleus and try to measure the mass by using a mass spectrometer, when mass is measured by a mass spectrometer, it is found that the mass of stable nucleus, so which I'll call it as Mn, sorry, which I'll call it as M, is observed to be less than the total mass of the nucleons. found, it is found that the mass of the stable nucleus M is less than the total mass of the nucleons. So what I'm trying to conclude or say from here is mass of the nucleus is actually less than Z times MP plus A minus Z times Mn. And why is this happening? It is because of a parameter called as binding energy, about which we will discuss next. But before that, the question is, if I am able to calculate this M, if I am able to calculate Z times MP plus A minus Z times Mn minus the actual mass, then this will give you a small difference, delta M, and this delta M is given a name called as mass defect, which is a very, very, very important term in this chapter. So it's called as mass defect, and its definition goes like this. And its definition is difference in total mass of the nucleons and actual mass of the nucleus. So this is the total mass of the nucleons, and small m represents the mass of the nucleus. So if you are able to calculate this difference, that difference is called as delta M, which is also known as mass effect. Okay. And the last property that we have is called as binding energy, which has something to do with the mass defect. So about this, I will start tomorrow. Okay. So otherwise, things are clear.
Yes, sir.
Okay, good. So if it's the case, we'll wind up.
Thank you, sir.
Thank you, sir.
Thank you, sir.